We always see the concrete and the steel go up, right? But have you ever actually stopped to wonder what happens to the earth right beneath your feet before a massive new highway or a sprawling mining megaproject gets built? What about that complex living foundation it's all resting on? Well, welcome to this explainer. Today, we're basically playing detective. We are diving into the, frankly, fascinating world of soil conservation and environmental impact assessment studies, or EIAs. We're going to see exactly how experts analyze the ground, how they predict the physical and chemical impacts of these huge developmental activities, and then how they design these brilliant measures to prevent soil degradation. It is literally a ground-up investigation.
So here's a quick look at our roadmap for today. We're going to cover the soil conservation expert, establish our ground baseline, get into the soil forensics, evaluate erosion and land capability, predict environmental impacts, and wrap it all up with the soil management plan. Let's get into it.
Section 1. The soil conservation expert, our lead investigator.
Okay, so every great investigation needs a top-tier detective. And in the EIA world, that's the Functional Area Expert, or FAE, for soil conservation. And look, they aren't just casual observers out there with a clipboard. The accreditation here is intense. We are talking about highly specialized individuals holding master's degrees in agricultural sciences, soil sciences, earth sciences, or even civil engineering. They're uniquely trained to assess potential impacts across the entire lifespan of a project, from figuring out soil fertility to fully designing remediation plans for contaminated land. The FAE is the lead architect making absolutely sure a new project doesn't just irreversibly destroy the site.
Moving on to Section 2, establishing the ground baseline, basically processing the scene. So, before anyone can predict the future of a site, our expert has to understand exactly what the soil looks like today before a single shovel hits the dirt. And you can't just scoop up some dirt in a jar and call it a day, right? The sampling protocol is rigorous. The FAE has to identify a minimum of 5 to 8 different locations across the site, strictly mapped out with GPS coordinates. Then, they extract what are called composite samples. This means they mix topsoil from 0 to 15 centimeters deep with subsoil from 15 to 30 centimeters deep. This gives us a truly representative profile. Finally, these samples are securely logged and shipped off to a heavily vetted, NABL-accredited laboratory, so the data is completely bulletproof.
But wait, even before those samples leave the site, the FAE is already gathering physical evidence. They'll determine the exact soil color using a standardized Munsell color chart. They literally get a feel for the earth right there in their hands. Is it sandy, loamy, heavy clay? They're also mapping out the topography. Is it flat, rolling hills, coastal? And they document the current land use. Because if there are already signs of, say, waterlogging or wind erosion, the expert needs to note that immediately. This physical evidence totally frames the rest of the investigation.
Section 3, Soil Forensics and Analysis. Time for the lab results. All right, so we're indoors now, unmasking the hard quantitative numbers. The first big result is the exact soil texture analysis. Our expert felt it on site, sure, but the lab uses pipettes and hydrometers to break it down into precise percentages of sand, silt, and clay. And why does that matter to us? Well, because a high clay soil traps water and gets compacted super easily, whereas a really sandy soil might let toxic contaminants drain way too fast right into the groundwater below. Simply put, texture dictates behavior.
Now let's check out the physical-chemical parameters. You can think of these as the soil's vital signs. The lab tests for pH. Ideally, we want that sitting in the 6.5 to 8.5 range. They measure organic carbon, which is literally the lifeblood of soil fertility. Anything over 0.75% is a great sign of healthy, productive earth. But a really crucial one here is bulk density. Normally, it sits between 1.1 and 1.6 grams per cubic centimeter, and it basically tells us how compacted the ground is. If a massive construction project compresses that soil too much, the porosity, which is normally 40 to 60%, just plummets. Water and plant roots can't penetrate it anymore. It essentially suffocates the ground.
100 milligrams per kilogram. Okay, this is a critical red line number in our forensics. It represents the absolute maximum acceptable limit for lead during heavy metal screening. The lab goes hunting for toxic elements, arsenic, mercury, cadmium, lead, just to establish that baseline. If the soil is already contaminated, or if the proposed project threatens to push these numbers past safety thresholds, the entire environmental management plan has to pivot instantly to contain that massive risk.
Which brings us to Section 4, Erosion and Land Capability. Let's evaluate the threat.
With all these lab results, our FAE evaluates the land's inherent capability using the Land Capability Classification, or LCC. This system drops the land into buckets from Class 1 to Class 8. Class 1, dot is prime. Very good arable land with zero limitations. The kind of farming soil you desperately want to protect. On the total opposite end, Class 8 is non-arable. Super extreme limitations. Basically only good for wildlife or recreation. By locking in this classification, the expert can tell project planners exactly what's at stake if they build over it.
Now, to assess the risk of this soil literally just washing away, we use the Universal Soil Loss Equation, or USLE. And guys, this isn't guesswork, it is strict mathematical modeling. A represents the estimated annual soil loss. To find that, we take R, which is the rainfall erosivity based on local weather, and multiply it by K, the inherent erodibility of the soil we just found in the lab. Then we factor in LS for the length and steepness of the slope, C for the vegetation cover that's already there, and P for existing conservation practices. When you run this equation, it predicts exactly how many tons of soil per hectare will wash away every single year if we leave it unprotected. It's kind of a game changer.
Section 5. Predicting environmental impacts. It's time to calculate the project's toll.
So, we have our baseline, we have our erosion models. Now comes the really tough question. What actually happens when the heavy machinery shows up? We have to compare the before and after. On the left here, we've got those healthy baseline conditions we just mapped out. Normal bulk density, thriving organic carbon, totally safe heavy metal levels. But on the right, that's the predicted toll. If we don't mitigate it, the sheer crushing weight of those machines will cause severe soil compaction, driving that bulk density way up. Stripping the land causes a total loss of topsoil fertility. And a single accidental chemical spill, that's a severe contamination risk.
So the FAE meticulously itemizes these degradation risks. They quantify exactly how much water and wind erosion will increase when the vegetation gets ripped out. They calculate the severity of compaction in high-traffic zones. They map out the potential pathways for a fuel spill, and they measure the exact anticipated loss of vital organic nutrients. And I want to be clear here, this isn't about just stopping development. It's about anticipating absolutely every single way the Earth could get damaged so we can build safeguards right into the project from day one.
And that leads us to Section 6, the Soil Management Plan. This is how we save the Earth. Because our expert has predicted the impacts so carefully, they get to write the resolution to the case, the Soil Management Plan. And in this plan, topsoil is basically treated like biological gold. I mean, considering it can take up to 500 years just to naturally form a single inch of topsoil, you can see why the preservation strategy is so strict. The plan tells construction crews the exact depth to safely strip the topsoil, it gives them precise GPS coordinates for safe stockpiling, and crucially, it strictly caps the height of those stockpiles. Why? Because if you pile it up too high, the sheer weight crushes and kills the living microorganisms at the bottom. Finally, they wrap those piles in silt fencing and tarps with a firm mandate to reuse that living soil later, whether for landscaping, green belts, or giving it right back to agriculture.
But it's not just stockpiling. Look at the dynamic, site-wide conservation measures they deploy. For slopes where that USSLE equation predicted crazy high erosion, the plan mandates physical terracing and contour bunding to break the speed of the water runoff. While the bulldozers are active, silt fences and sediment traps act as physical barricades so the soil doesn't just wash off-site. Any exposed dirt gets stabilized quickly using hydroseeding, which is basically spraying a slurry of seed and mulch directly onto the ground so it takes root fast. Plus, comprehensive drainage management makes sure stormwater doesn't pool up and ruin the site.
The thing is, a true soil detective's work doesn't end when the ribbon is cut. The management plan mandates a robust post-project monitoring plan. Long after those construction crews pack up and go home, the project proponent still has to extract samples and send them to those NABL-accredited labs. They have to continuously track the pH, the organic carbon, heavy metals, and erosion rates at those original baseline spots. It's the ultimate accountability check. It guarantees that the mitigation strategies are actually working and that the Earth stays healthy year after year.
So the whole environmental impact assessment process really proves that massive development doesn't inherently mean environmental destruction, as long as we have qualified experts doing the hard forensics and enforcing these strict conservation plans. It shows us that soil isn't just dirt, It's this incredibly complex, fragile, living ecosystem. So as we keep expanding and building and pushing forward, I just want to leave you with this final thought. We build our future on the soil of today. Are we doing enough to protect our foundation? Thanks for joining me on this explainer, and we'll catch you next time.